Yes. Is my screen visible to everybody? Yes, someone please respond.
Yes, sir. Yes, sir.
Okay. Sorry. So we'll continue. So in the previous class, we have started with the design of Intz tank, and we have gone through the IS code procedure, and we have designed the top dome and the top ring beam. And if you remember the top dome, we are considering the thickness of the top dome as 100 mm. Rest of the dimensions we have already calculated prior to the design of top dome, and based on the dimensions of the top dome and the loading, we have also designed the top ring beam, which is subjected to a hook tension. Okay. Now the most important part which we are going to design today, this is the cylindrical wall. Okay, so this cylindrical wall has to be designed as per the codal provisions. So it has to be designed for the hook tension, for the bending, as well as for the shear. Okay, so if you go back, you'll find that we have taken the dimensions like this. Okay, so the height of this we have taken, it was 7.54, which we have rounded off to higher side. So the height of this particular cylindrical wall, we have taken this as 8 meters, and the diameter of the cylindrical wall was 12 meters. Okay, so with these dimensions, let us start with the design. So here, this is the h value. Okay, so this is the h value, and this is the diameter value. Okay, so usually what we do is we assume the thickness of the wall. Okay, so in general we write thickness of the wall is 30 times h plus 50. So the height of the wall is basically your 8 meters. Okay, so 8 into 30 plus 50, so this comes out to be something like 290 mm. So this can be rounded up to in the multiples of 100 mm, so this can be taken as 300 mm. Okay, so this is my assumption. This assumption may go wrong, or it may be right. So we will have to see based on the design. So for this cylindrical wall, like I said earlier, we have to design this for hook tension, then the bending, as well as the base shear. So for this purpose, we need the value of h square by dt. Okay, so this is h square. So height value, we are taking this as 8 square divided by the diameter is 12, and the thickness we have assumed over here as 300 mm. So this should be now zero point 0.3. Okay, so can somebody give me the value of this h square by dt? Yes, anybody? Yes, students. H square by dt value. Please take out your calculators and give me the value of h square by dt.
17.78.
Okay, so this is 17.78. So you can see the available range in IS 3370 part 4, because if you remember, we have to design this particular wall for hook tension using the tables, table 9, 10, sorry, 8, 9 and 10, which are there for hook tension, bending and the base shear. So if you refer those table, you will find the range of h square by dt is given in the range of 0.4 to 16. So you can see this is the value of h square by dt is basically greater than the this is something like 17.78. Okay, so this is not in the range, so we cannot use this particular is code. Okay, so in this particular case, what we are going to do is we'll find the what will be the pressure at the bottom. So this is a pressure diagram. So the height of this wall is 8 meters. So bottom pressure will be hw, that is height of the water, multiplied by the density of the water. So this is 80 and density of water is 10. So this is going to give me 80 kilonewton per meter square. This will be the pressure which is coming at the base of the wall. Okay, So the hoop tension is nothing but the pressure multiplied by diameter divided by 2 or radius. So basically the pressure over here is 80 and the diameter is 12 divided by 2. How much is this? Somebody please tell me.
480.
480.
Yes.
This is 480 kilonewton. So this is a very large value as far as hoop tension is concerned. Okay. So let us try to design the wall for the maximum hoop tension. Okay, so this hoop tension will be something like 480 into 10 to the power 3. Okay, sigma st will be something like 130. How much will be this ast?
3692.31.
Millimeter square. Okay, then we have to see whether it is less than ast minimum or not. I'm sure ast minimum value will be less. So this is 0.24% of the cross section area, where your cross section area is basically 300 into 1000. Okay, so how much is this ast? 0.24% of 300 and 300 multiplied by 1000.
720.
720. Okay, so this is very less. Okay, so we are going to consider this, we are not going to consider this. Okay, so what we will do, we can provide say 20 diameter bars. Okay, so if we provide 20 dia bars, okay, okay, what will be the spacing for 3692.31 square? Yes. Yes, anyone? बोलो बेटा. 20 dia bars, what will be the spacing for 3692 millimeter square cross section area?
So 308.
308. This is a spacing, right? So we
Yes,
can
sir.
go for 300, isn't it? Because the thickness of the slab is, sorry, thickness of the wall is 300 center to center. Okay, sorry, thickness is 300, so we can definitely go for 300 center to center. Okay, so now we will see whether this particular wall is safe in tension or not. So for this we have to calculate the equivalent area, which has to be kept in the denominator, and the numerator we have the maximum hoop tension. So maximum hoop tension is 480 into 10 to the power 3. Now the area of the concrete is basically 300 into 1000. Okay, m is I think 10.98 if I'm not wrong. Okay, and this is pi by 4 into 20 square. This is the area of the bar, and this is kept at 300 center to center. Okay, so can somebody give me what will be the tensile stress in the concrete due to this pressure?
Point 0.35.
0 point. Are you sure? Someone please cross check. कितना आ रहा है? Yes, someone.
Or that spacing is not 300, it's 85.
Sir, हाँ spacing में थोड़ी गड़बड़ हुई है sir. It should be 85.
Okay, so let me make some changes then. Okay, so this is 85 you are saying, right?
Yes, sir.
Okay, so anyway, so this is 85, so can I make it 75? Okay, so let us make it 75. Okay, anyway, this is not going to become safe.
So
Please cross-check.
1.38.
1.38. Okay, so you see this is basically the value of actual stress in concrete is greater than the permissible stress in concrete in direct tension, which is 1.3 for M25 grade concrete. Okay, so basically what I'm trying to say is the wall thickness which we have assumed, that is 300 mm, it is not at all safe as far as the hoop tension is concerned. Okay, so in this particular case, now what we have to do is we have only one option: either we increase the thickness or we can go for increasing the steel. But you see, we are already providing that 20 dia bars we are providing, and that too at 75 center to center. It is already a very I mean expensive affair as far as this steel is concerned. Okay, so it's better if we increase the thickness of the wall itself. Okay, so now what we can do is we have to do the entire analysis. So now in this case we can take the h value as h. This is fixed, the diameter is 12 but this time now let us take the thickness as 350 mm. Okay, so now your h square by dt value, so this is h square by d and t, so h will be 8 square, diameter will be 12, and the thickness will be now 0.35. How much is this? H square by dt, someone?
15.23.
Okay, so 15.23. Now if you refer table number 9 of IS 3370 part 4 1967, this is table which is given to compute the hoop tension. Okay, so here the value is now lying between 14 and 16, so the exact value over here it is 15.23. Okay, so now for hoop tension, let us find out where is the maximum hoop tension which will be occurring. So here you see this is increasing, this is also increasing, this is increasing, this is increasing, this is also increasing, this is increasing. Now this will be the maximum value, because you see further this is going to get reduced. Okay, so this is the maximum value for 14, and as far as the row of 16 is concerned, that is this row, you will find the maximum value is also there at 0.7 h. Okay, so now you have to interpolate the coefficient between 16 and 14 for 0.7 h for the h square by dt value of 15.23. Okay, so can you do this? Okay, so this is for 14, we have 0.6666. Okay, and this is for 16, we have 0.687, and I want what is the value of 15.23. Okay, please give me the coefficient.
So 0.6789.
0.6789. Okay, now as far as the equation which is given in the IS code is concerned, the maximum hook tension can be calculated by a simple expression which is given over here, that is coefficient into W into H into R, where this coefficient is now interpolated coefficient, that is 0.6789. The this is nothing but the density of the water, which is 10, the height of the water it is 8, and the radius, so radius is nothing but we have the diameter is 12, 12 divided by 2. Okay, now how much is the hoop tension? Please somebody tell me the value of hoop tension.
325.87.
Okay, this is in kilonewtons. Okay,
Yeah.
so earlier if you see, the value of hoop tension was very high, that is 480. Okay, but now since we are using this table, and that too the thickness is now increased, so there is a tremendous reduction in the hoop tension, and you will find the maximum hoop tension value is 325.87, and at it is acting at a distance of 0.7 h. Okay, so if you remember, your hoop tension is going to create a shape which is something like this. Okay, so here, which is measured from the top, so at 0.7 h you are going to get the maximum hoop tension. Okay, so this animated videos we have already seen in the design of GSR. Okay, so now see, this particular wall is having height of 8 meters. Okay, so what is going to happen, if we know the what is the value of AST for the maximum hoop tension, we cannot provide the same AST value throughout its height, because height is too much and your structure will be over safe and it is going to cost us as far as the steel is concerned. So what we are doing over here is we are going for the intermediate AST calculations, and accordingly we have to provide the AST. Okay, but before providing the actual AST, first of all, we will have to see, or rather, we will have to check whether the given this hoop tension, or whatever hoop tension we have calculated and whatever thickness we have assumed, whether it is sufficient for direct tension or not. Okay, so let us check for that. So maximum hoop tension was 325.87. So this value is 325.87 into 10 to the power 3. Okay, sigma st is now 130. How much is the AST which is required over here? Yes,
2506.7.
25
06.7.
millimeter square. Okay, now we have to go for AST minimum, that is 0.24% of cross section area. Now this time cross section area is 350 into 1000. Okay, how much is this? I'm sure this will be less than AST required.
840.
840. Okay, so we can go with this. Okay, so if we provide 16 dia bars, okay, what will be the spacing for 2506 square?
Sir, 80.
Sorry,
80.
80.
80.20.
Okay, so we can provide this as 75 Okay, so this is okay, or otherwise you can provide 20 dia bars and then the spacing can be even increased.
So for
Okay,
20 it is 125.
sorry.
For 20 it is 125.
ओके, हमने कितने दिए एट द एंड 16 ही दिए. ठीक है, we'll go with 16. Okay, it will be better. Okay, why, I'll tell you after some time. Okay, so now uh, we have to check for the tensile stress. So the maximum hoop tension which is occurring, this is 325.87 into 10 to the power 3. Area of the concrete is 350 into 1000. M value is 10.98, and this is AST is 16 dia at the rate 75 center to center. How much is this? Tensile stress in concrete in direct tension, actual stress.
So 0.85.
0.85. Okay, Newton per square. Okay, so now you can see it is less than the permissible limit, so we can say yes, for maximum hoop tension the 350 thickness wall is sufficient enough to resist the hoop tension. Okay, so now here the actual calculation starts. So I want everybody to pay attention on the screen. So what I have done over here is, here I have written a table which was given in the IS code. Okay, so this was a portion of the IS code, so same values I have given over here. So h square by dt value for 14. Okay, and here I have gone for h square by dt value for 16. Okay, now this was the actual h square by dt value which we have received, that is 8 square divided by diameter is 12 and thickness is 0.35. Okay, so this is 15.2381. So I have gone for the interpolation of the values between 14 and 16 at every intermediate level, that is for 0, 0.1, 0.2, 0.3, so on up to 0.6, and there will be a at the bottom. Okay, so I have calculated all these coefficients over here. Okay, then after calculating the coefficients, I have calculated the hoop tension. Okay, so hoop tension is what? Coefficient into W into H into R. This is already given in the IS code, and same value we have used over here also. Okay, so you can see at the bottom. Okay, over here you can see coefficient into W into H into R. So accordingly, I have calculated the hoop tension. Okay, then once the hoop tension is calculated, I am going to calculate what is the AST which is required. Okay, and AST, how you are going to calculate? Hoop tension divided by sigma st. Okay, so at every level I have calculated the AST. Okay, so you will find the AST which is required for maximum hoop tension, that is at 0.7 H. We have calculated this value something like 2506. Okay, so you'll find 2506 somewhere over here. Okay, I'm getting 2507, but anyway, that's not so there is a marginal difference, so no need to worry about that. Okay, so I have calculated the AST value at every level, and here I have written how much is the AST which is required for AST minimum criteria. Okay, so the maximum of these two, okay, maximum of these two I have written in this particular column. So here for 0H, that is at the top, I am going to provide the AST minimum. Here also AST minimum, here also AST minimum, but from this point onwards I am going to provide how much is the actual AST which is required. Okay, so accordingly now I have to decide what kind of reinforcement has to be provided. Okay, now since this reinforcement has to be provided in the circumferential manner, because this is in the hoop tension, I am going to provide the double spacing. Okay, so double spacing means what? If I have a wall over here, I have wall over here, so I am going to provide one bar over here, one bar over here, one bar over here, and one bar over here. Okay, so this much spacing will be the double spacing. Okay, now remember over here we have calculated 16 mm dia bars at 75 mm center to center. Okay, so what I am going to do is this 16 mm dia bars at 75 I am going to keep like this. Okay, but here this will be 150, and from here to here this will be 150. So I am going to provide alternate bars each on the both the faces. Okay, that's why you will find here I have provided for maximum AST 16 mm dia bars at 150 mm center to center. Okay, I hope this is clear to everybody. Is it okay?
Yes, sir.
Okay, so this type of exercise you will have to do because the height of the wall is too much, that is 8 height is there, so we have to go for optimization. Okay, so as a result of this, what you will find that 8 mm dia bars at 100 mm center to center is required for the almost 1/3 of the portion which is measured from the top. Then we have one more section, this is 10 mm dia bars at 125 mm center to center, and remember this 125 mm center to center is on both the sides. Okay, that is on one side it is also 125 and on the other side also it is 125. Then we have one more section over here at 10 dia at 100 mm center to center. Then here it is 16 dia 200 mm center to center. Then from here to here 16 dia 150 mm center to center. Then we have 16 dia 75, and we have 8 dia 100 mm center to center. Okay, so like this you have to prepare a drawing giving all the distances and all the detailing, that is 8 mm dia or 10 mm dia or 16 mm dia, whatever is the double spacing. Okay, so this preparing this table, it takes a significant amount of time because we have to first of all find out the interpolated values. Okay, and then we have to calculate the hoop tension, AST, and so on. Therefore, it is a time consuming process, but otherwise you can use Excel for doing this. Okay, so have you understood this? Are there any queries? Yes, students, are there any queries? Shall I continue? बोलो भाई.
Yes, sir.
ठीक है. So this was the hook tension part. Now let us talk about the bending. Okay, so for bending we have to use table number 10 of IS 3370 part 4 1967, and here the h square by dt value will remain same. So this is 8 square divided by 12 into 0.35, so this is coming out to be something like 15.23, isn't it? Okay. So here we have to see the bending. So here we have to go for the interpolation between 14 and 16 as per the table. Now for the time being, if you see the table, there are some values with negative sign and there are some values with the positive sign. Okay. So for the time being, you just forget about this sign, and if you focus on the magnitude, so for this 14 table, 14th row, here you will find this value is the maximum value and it is a positive bending moment. Okay. As far as, no, this is not the one, this is the last value. Okay, because this is negative 0.009. Okay, and this value is 0.002. So definitely as far as magnitude is concerned, this is the maximum value. Okay, so this is a negative bending moment and this is a maximum positive bending moment. And if you see the row of 16, there also you will find this is the maximum positive and this is the maximum negative. Okay, so we have to design the wall for the maximum bending moment irrespective of whether it is positive or whether it is negative. Okay, so we will be focusing on the magnitude, not on the sign. So you will find the maximum bending moment is there at base, that is 1h. Okay, so all you have to do is just interpolate the value, that is say for 14 we have 0.009, and for 16 we have 0.0079, and in between we have 15.23. Okay, so can somebody do the interpolation and give me the value of coefficient?
0.0083.
0.0083.
83.
Okay. Now, in the same table, equation is given to calculate the maximum bending moment. So this equation will remain same. The density of water is 8 and height is, sorry, density of water is 10 and height is 8 cube. Okay. Give me the value of maximum bending moment, please.
42.50.
42.5 kilonewton meter. Okay. So now we have to check for the bending stresses also. So the maximum bending stress can be calculated as maximum bending moment divided by I into Y. So maximum bending moment is 42.5 10 to the power 6. I is BT cube by 12. So where B will be your 1000. Okay. Into this will be 350 to the power 3 divided by 12, and your Y value will be 350 divided by 2. How much is the bending stress?
2.08.
Okay, now you see what has happened over here. So the actual bending stress which is there in the wall is 2.08, whereas the permissible bending stress which is there for M25 grade concrete, it is 1.8 only. Okay, so now what should be done? Can anybody tell me? क्या करना पड़ेगा? Yes, yes, speak up. क्या करेंगे? बोलो. Yes, anybody? So for the first time you find that the bending stress is out of the limit. So now the factors which are influencing the bending stress is first of all the bending moment. Okay, somehow we have to reduce the bending moment, or we can increase the thickness. Okay, so if we increase the thickness, this is going to help us. So since this is not safe, okay, so we have to increase the thickness. Okay, so for this purpose what we have to do is you have to redo the entire calculations. Okay, तो पूरे calculations आपको repeat करने पड़ेंगे. You have to go back up to here. Okay, you have to calculate the hook tension one more time, because now your thickness will not be sufficient. This 350 mm will not be sufficient. Okay, you may have to go for even 400 millimeters. Okay, you have to redo the calculations for hook tension, whether it is safe or not. Then you have to go for the bending one more time. Okay, and then you have to continue further. Okay, have you understood this? Yes, students, have you understood this? Yes, Hardik, Rashmi, Rutuj, Kunal, Om, Radhika.
Yes, sir.
ठीक है?
Yes, sir.
So you see, you have to redo this thing. Okay, so for time being I am not doing this, but in actual practice you have to do this. Okay, remember this. Okay, just for academic purpose I am continuing the old value of bending moment and I am continuing the design, but ideally you have to redo it. Okay, again I am saying you have to redo the entire design right from the calculation of the hook tension. Then you have to redo the calculation for bending moment. Okay, just for academic purpose I am continuing the problem, and I am continuing with the same bending value, that is 42.5 kilonewton meter. Okay, so for this how much depth is required, that I am going to calculate. This is 1.527, b will be 1000. Okay, how much b is required now for this much of bending moment? Yes, please tell me the value of bending moment.
So 166.
166 बहुत कम आ रहा है. Is it so?
Yes, sir. 166.83.
Okay, the stresses may not be same, but the required thickness is less. Okay, anyway, so since this is 166 and it is having the wall is basically in contact with water, so we have to provide some greater cover. So usually we provide 25 mm, but since it is in contact with water, so we can go up to say 40 mm. Okay, so this is going to be something like this will be 206 mm. Okay, so this is the total depth required, and how much actual depth we have provided? We have provided something like D is 350 mm. Okay, so this will be revised. Okay, so when you redo the calculation, this depth will be revised. Okay, so for the time being, I am continuing this. Okay, so if we go for this, so the final value of D will be something like 350. Okay, and you can have the small d as 310. Okay, so for AST calculation, so bending moment I am keeping the same, that is 42.5 10 to the power 6. Sigma ST is 130. How much will be the value of J and D? J value कितना होता है बेटा? 0 point, मैं भूल गया.
0.86.
86.
0.86. Sorry.
0.86.
Okay. Give me the AST value and also give me the AST minimum value. I think this is 480 if I'm not wrong, for 350 mm.
So 840.
Sorry,
840.
840. Okay, not 480, it's 840. Okay. How much is AST?
1226.26.
Sorry.
1226.26.
Okay, so definitely we are going to use this. Okay, and this reinforcement has to be provided in the vertical fashion. Okay, so how much will be the spacing for say 16 mm dia bars? Also calculate the spacing for 12 mm dia bars.
So for 16, it is 164.
And for 12,
Sir, 92.23.
92.
okay, so I think we can go with this. Okay, that is 16 dia at 150 center to center. Okay, and this reinforcement has to be provided in the vertical fashion. Okay, and there will not be any optimization because the reinforcement, like since it is vertical in nature, you cannot reduce or decrease the diameter. Okay, so we have to provide throughout its length, and if it is required we can go with two different sections, and at the top and at the center, or you can divide this into half, two parts. So at the top we can provide different spacing, at the bottom we can provide different spacing if it is possible. Okay, otherwise usually we provide the same spacing. Okay, so this completes the bending part. Now the only part remaining, which is in the shear. So we have to see if the structure is safe for the shear, which is caused due to the horizontal pressure. So the shear force has to be calculated from table number 11 of IS 3370 part 4 1967. Again, it is depending on h square by dt value. So this is h square by dt value is 15.23. Okay, I think 15.23 के जगह अभी हमको थोड़ा सा दूसरा वैल्यू लेना पड़ेगा, because I have done the calculations in the background, and what I found that the thickness of 400 mm is sufficient. Okay, so your h square by dt value will be, h value will be 8 square, d value will be 12, and this will be 0.4. How much is the h square by dt value? कितना आ रहा है?
13.33.
13.33.
33.
Okay, so your 13.33 comes over here. Okay, so this is 13.33. Okay, so for this you have hoop tension, this will be safe, and your bending will be also okay. So for this thickness you have to redo all the calculations. Okay, so I'm going slightly faster for that, right? So if you refer this table number 11 of IS 3370, Part 4 1967, you have to refer the column of triangular load with fixed base and you have to interpolate the coefficient. Okay, so can anybody give me what is the coefficient? Yes, 13 0.13.
0.138.
0.1416.
0.138. Okay, now in the same table the shear force value has to be, the equation is given, so the its coefficient into W into H square. So coefficient is 0.138, density of water is 10 and height is basically 8 square. How much is the horizontal shear force?
$88.32.
Okay, so this is 88.32 kilo Newton. Okay, so now we have to calculate the shear stress, actual shear stress. So this is something like 88.32 into 10 to the power 3. Okay, the width will be, let us say, 1000. The D value, okay, because you see capital D, we are taking this as 400. Okay, 400. So we can take 40 as clear cover. Okay, so your small d will become 360. Okay, how much is the shear stress?
0.24.
0.24 Newton per mm square, and this has to be less than the tau c value. Okay, now the tau c value is totally depending on the percentage of steel, and your steel percentage, you have to take the vertical steel. Okay, vertical steel means what? When we have designed it for bending. Okay, so right now the design is not available because every design we have done in the previous slides, this was for 350 mm. Okay, so I'm sure you will do it for 400 mm, and for 400 mm whatever AST you have provided, you have to find out the percentage of that AST over here, and based on that you have to calculate the value of tau c, and I'm sure you will always find that tau v is less than the tau c. Okay, that means the actual stress is less than the permissible stress, therefore the wall will be safe in the shear. If the wall is not safe in the shear, then either you can increase the thickness or you can increase the percentage of steel. Okay, so finally, you have to draw a very perfect figure for this. And remember, we have taken the thickness. Okay, thickness we have taken as 400 mm. Okay, so since this height is basically 8 meters. Okay, so what we can do is we can provide the section which is like this, that is the thickness over here, this can be 400 mm, which can be reduced up to 200 mm at the top. Okay, so this is going to cost you some less concrete, and it will be also safe in the bending as well as in the hoop tension, because as you move up, okay, your bending is also reducing and your hoop tension is also reducing. Okay, so like this you can provide the reinforcement. You have already seen, you can see the reinforcement details in this particular figure. So like this you have to draw a very accurate, very perfect picture, and in that you have to mention that how much is the spacing which is required at this level, at this level, at this level, because we have already divided the wall into segment, say various segments, and according to the segments we have to provide the reinforcement. Okay, and you can see the reinforcement are provided on both the sides of the wall, as far as the hoop tension is concerned as well as the vertical reinforcement is concerned. Okay, I hope this is clear to everybody. ठीक है?
Yes, sir.
Okay, so we will stop over here. Okay, and we will continue in the next class. So I expect that everybody will do the redo the calculations for the bending moment as well as for the hoop tension for 400 mm thickness. Okay, so this is a kind, it will give you a kind of a practice for designing the container wall. Okay, so let me take your attendance quickly.